with a standard growth. And then Sunday, I'm going to non-standard growth problems. Can you see the screen? Okay. So no problem?
Yeah. It's okay.
Okay. So this is about so-called Calderon-Digmund theory. And if we look at this very basic Laplace equations in the divergence form, this is elliptic, this is parabolic problems. So from this PDE, so it is clear from this non-homogeneous term F is under control by gradient U. So the classical Calderon-Digmund theory tells that if F belongs to LQ space, then gradient U belongs to LQ space for every Q bigger than 1. Okay, so it is due to Calderon-Digmund in 1952 for the elliptic case, and to Calderon-60 for the parabolic case. Okay, so the thing is then from we have a integral representation formula, like this is gamma is fundamental solution under the convolution. This is a differentiation with respect to xi variable. Then I have the solutions. Then the gradient U is homoattributable. This is like a Calderon-Digmund kernel. And this is bounded from L2 to L2 space gradient U, and from L1 to weak L1 estimate. Then interpolation gives us to the Calderon-Digmund theory. Okay, so then I am looking at like this is a variable coefficient. Like I have the matrix here. So the structure goes to omega and the matrix. Omega is a bounded open domain in Euclidean space. And the matrix is uniformly elliptic and bounded. Then the question is, what is the minimal requirement on the matrix? And the lowest level of a geometric condition on bounded omega, under which we have this kind of Calderon-Digmund estimate. And this estimate is for all Q, for every Q. So we expect that Q is very close to 2, then we don't need any extra conditions. But as Q is getting larger and larger, then we need some kind of regularity requirements. And the question is, what is the optimal one? Okay. So the basic argument is was started from the Friesian argument. This is called to be constrict. We start with a priori estimate, like assume that the matrix is good enough, like at least continuous. And the domain is also nice enough, like C11 domain. And then we can localize by using cutoff function, just looking at small ball, and U is a solution in this small ball. Then we can transform the PD into this PDE. But the thing is that here, the left-hand side is Laplacian equation, because this is a constant coefficient. Then the standard of priori estimate goes, right? Gradient U arcunum is under control by, this is A minus AX0 L infinitum, gradient UQ plus F2L cunum, or like we can use this BMO seminum over the matrix. Okay, so if this is small enough, or this is small enough, then we have the desired estimate. Okay, this is a very basic idea. So here again, if this norm is small enough, or this norm on the BMO semi-norm is small enough, then we can obtain the priori estimate here. Yes. Once we reach here, then for the boundary estimates, just the flattening arguments and the covering argument, and the later approximation give us the Calderon-Zygmunt theory here. Okay. So let's go back to this major assumption on the coefficients. And this norm is small enough. This is true for the continuous coefficients if the radius r is small. And this is what happens if you want to LQ estimate with this method. That is a constraint method here. And the other case is a more general one. If the BMO semi-norm is small enough, this is what plays a crucial role in establishing LQ boundedness for the singular commutators that is naturally appearing in representation formulas. Like in early 90s, by these Italian mathematicians like Sciarrenza, Prasca, and Longo. Okay, so by using this kind of approach, so continuous coefficient is working. Like 66 by Mori, this is books, and the 72 and Zimendler, and 85 to 86, this Campanato. Actually, this is nonlinear problems with a linear growth. It looks like a linear problems. Okay. Then how about this continuous coefficient? In general, this kind of LP estimate cannot hold true, like by considering this example by like Mayer's is early 1960s. Okay, so if we look at, so this is n equals 2, the simplest one. If we define this matrix in this way, then we can easily check that this matrix is not continuous at the origin. But this matrix is uniformly elliptic and bounded. Also, this is a solution for the homogeneous problem. Then, by direct computation, we can show that gradient U belongs to LP only when P is strictly less than 4. If P equals 4, then it does not work. So this example tells us that we need to add some extra regularity requirement on the matrix beside this basic structure assumptions to ensure that the classical Calderon-Zygmunt estimate is valid. And the question is, what is the extra and the minimal regularity requirement? So, and the answer is a BMO space. So this is the typical definitions. It has bounded mean oscillation. And we can add this assumption, the bounded mean oscillation is goes to zero as the radius goes to zero. This is a vanishing mean oscillation. So this might be minimal assumptions on the coefficient. So let me tell you again about BMO space. This is so important in the regularity theory. So BMO means that functions having bounded mean oscillation. And this space is appropriate substitute for L infinite when L infinity does not work. Also, this comes very often in harmonic analysis, also interpolation theory. So let me tell you, BMO is the dual space of the Hardy space H1. And this BMO is very close to L infinite and the VMO. This is the relations. So BMO is most general. Then L infinite and the VMO. Okay, this is a very good counterexamples for their relations. Okay, so another good analytic tool is going to classical maximal function. Okay, this is the definition of the maximal function. Most of you know probably. So for the PDE on the bounded domain, so we need to define this kind of a restricted maximal function. And the good thing for the maximal function is that it is invariant with respect to scaling. It means that if you have one point, x0, and at that point, the value of this maximal function is less than 1, then you can say that f over x is really less than 1 in all scales. And another good property is that here, this is the upper level set of the maximal function. And this is just a function, upper level function. They decay roughly in the same way. Okay, so let me tell you more precisely. This is a weak 1-1 estimate. And this is a strong QQ estimate. It means that if f belongs to LQ, then maximal function also belongs to LQ. And also the same, maximal function belongs to LQ, then this implies that f belongs to LQ. So it's better for us to use this function instead. We better use this maximal function because it has more strong property like this one. Okay. So let's go back to the linear approach. This is the so-called singular integral operators. Actually, it goes back to Calderon-Zumwalt in 52. And then in terms of commutators, Cirenza and Prasco and Longo, that is for the VMO coefficient. But the thing is that in general, it does not work for a system of PDE or on very non-smooth domains. Okay, for the divergence structure in 96, also Italian mathematician Di Fazio, he has proved on the VMO assumption of the coefficient and the boundary is good enough, then Calderon-Zumwalt theory is proved. And later, it is extended to this C1 domains. So actually, my PhD thesis is starting from this kind of result. Okay, so let me go to the maximal function operator. So method of approximation making use of a C01, that is a Lipschitz estimate, and the maximal function. And then also, along with the Calderon-Zygmunt decomposition, and this approach is introduced by Caprelli and Ferrar in 98. And then, but the thing is that it works for the boundary estimate beyond the Lipschitz category. So by using this BMO space and the maximal functions, we are able to prove that LP estimate under the assumption that the coefficient has a small BMO semi-norm and the boundary of the domain is sufficiently flat. So let me tell you about the definition of a Liephenberger flat radar. Okay, then how about nonlinear elliptic problems like with a standard growth? Like this is a typical P Laplacian problems, and this P is bigger than 1 and less than infinite, some number. Okay, then the risk is how to show this Calderon-Zygmunt estimate. In this case, is Q is bigger than P. Of course, this constant is independent of solution and the non-homogeneous term F here. And then comparing from the linear problems, this difficulty comes from the fact that we cannot apply to any linear arguments. So we need a nonlinear approach there. And then starting for this nonlinear approach comes from Ivaninian is 83 found a purely nonlinear way to solve this issue, thereby proving for every Q bigger than 2P. Actually, this marks the beginning of the nonlinear Calderon-Zygmunt theory. And then the idea is starting from a priori estimate and by using the sharp maximal function. Sharp maximal function means that by using the function minus its integral average of the ball. And then use C1 alpha regularity for these homogeneous problems. This is in a certain sense to replace the representation formulas for these nonlinear problems. And then use the tools from harmonic analysis. And then Di Benedetto and Manfredo, they extended the Ivaninek's result to the case of systems, like 10 years later. Okay, and then here, the method of approximation by Caprelli and Ferrar, they have introduced a method of approximations, which is based on the maximal function and the perturbation arguments. And first, looking at the limiting PDE or the reference PDE, like a regularity result for a fixed off rate, that is homogeneous problems. Here, at least we expect the regularity is Lipschitz regularity for the double OMP theory. And then a local estimate of solutions to the given problems by comparison with the solution of the limiting PDE. And then a real variable arguments coming from Calderon-Zygmunt decomposition. Okay, so this is a perturbation plus harmonic analysis technique. And then later, Li Hye-Wang substitute the Calderon-Zygmunt decomposition for the Vitalin covering lemma. So this Vitalin covering lemma is working very well on the very non-smooth domains. So here is the P-Laplacian elliptic problems. So for a given number bigger than 1, suppose that this is a non-homogeneous term belongs to LP space. Then we look at this typical P-Laplacian type problems. Then the given data is we are looking at this domain and this nonlinearity. And then the solution is U. For the simplest case, like P equals 2, and this nonlinearity is G, then this reduced to Laplacian equations. And if A is like here, that is, this is a P-Laplacian problems. Okay. So again, before Professor Minzona actually introduced this structure assumptions for this nonlinear problems P-Laplacian. So let me say again, omega is just a bounded domain. And the nonlinearity is a characteristic, means that this is measurable in X and differentiable with respect to Cauchy variable. And assume that this is kind of this assumption. Okay, so this is elliptic and gross. And the good thing for this nonlinear elliptic problems in terms of a maximal function is that it has this scaling and the normalization property. So knowing that the maximal function is heavily dependent on the scaling invariance property, this FIDI is working. Okay. So again, under the basic structure conditions, we can further this kind of a closed condition and the monotonous assumptions. Of course, this is a little different constant, but it does not matter. Okay, so here is the definition. Weak solution is the standard definitions, right? We take a test function in the solution space, and then take integration by part. We have these weak formulations, and this is the definitions. So, of course, we know that by using the monotonicity property, there exists unique weak solutions for these problems, provided just omega is bounded. And the nonlinearity satisfies just the basic structure conditions. Then we have this standard energy estimate. And again, the problem is the same as in the linear case. So you want to ask what is the weakest conditions to place both on the nonlinearity, in particular this X variable, and what is the lowest level of a geometric structure on the boundary under which you have this kind of relation with this Calderon-Zygmunt estimate. Okay, the question is the minimal assumptions on the linear problems can be also applied to this nonlinear problem. Okay, so again, we have used the same assumptions. Like this is a BMO, small BMO assumptions. So if we look at this nonlinearity, it has these gross conditions in terms of Cauchy variables. And it has a small BMO semi-norm. Then we that it should be working. So let's go back to our domain that is called to be Liephenberger flat domain. So Liephenberger flat domain means that at each point on the boundary and at each scale R, then we can find a local coordinate so that in this U coordinate system, the part of the boundary can be trapped into two hyperplanes. Okay, so the definition is very clear. So it means that the boundary of a delta Liephenberger flat domain is very rough. This is a geometric condition exhibiting a very low level of regularity, prescribing that under all scales, the boundary can be trapped between two hyperplanes, depending only on the chosen scale. So this domain is perfectly matching with the PDE having invariance property under the scaling. So this is some summary about the Liephenberger flat domain. Actually, this domain was introduced by Liephenberger in 1960s when he studied the minimal surface theory like plateau problems. And the domains go beyond the Lipschitz category, means that not necessarily given by graphs. Also, from the geometric point, its boundary is locally close to disk in all scales. Also, this domain appears very often in harmonic measures and the geometry method theory, also pre-boundary problems. And the good thing is that the boundary can be fractals. And the fractal means that it is a geometric shape that exhibits a self-similarity across all scales. So, okay, so here is a main theory. So Q is strictly bigger than P, any number. Then there exists a small delta and a universal constant such that it means that the nonlinearity has a very small BMO semi-norm and that the domain is Liephenberger flat. It means that very flat in the sense of Liephenberger. Then I can claim that gradient U belongs to LQ space. And this, with this kind of this is the coherence instrument LQ estimate. Okay, then how we can prove this one? So the main approach here is by using maximal function approach. So by considering a normalization, by multiplying this small constant delta in a nonlinear way, we assume that the LQ norm over F is small enough delta. And then, so for some universal constant, we can find this universal constant. Here, the upper level set of gradient UP of the maximal one under maximal function. This is a big universal constant. The measure is sufficiently small. So whatever, we need this kind of smallness to use Vitaline covering lemma. And then recalling that our assumption, small BMO semi-norm, and also we recall the sufficient flatness of the boundary. And then using our hypothesis from Vitaline covering lemma, this means that if I have one good point under this maximal function, gradient u. And we have also the right-hand side here. The non-homogeneous term is sufficiently small in the pointwise way. So by using this maximal function, we can claim that gradient u is really bounded. Also, the right-hand side is almost zero. It means that our problem is very close to homogeneous problems. And then we look at this limiting PDE, like the right-hand side is zero. By looking at this assumption, f is sufficiently small. And then my domain is sufficiently flat. This is a very flat domain. Then we can see that my solution u is very close to the solution of the limiting PDE. And also, I have this assumption, gradient u is really bounded. Then I can use this is using ellipsis regularity for the limiting PDE. So the gradient v is really bounded for the universal constant. And then prove that one good point, like 0, implies most of a good point in the major portion of the small area. Okay, actually, this is the second hypothesis for the Vitalik covering lemma. So once we observe this one, then we can apply Vitalik covering lemma. And then do iteration. I have this kind of power decay estimate for this upper level set there. So once I reached this kind of a power decay estimate, then do computations. The LQ norm of gradient u is bounded by this one. And this is, as you see, this is a geometric series. So if I take this number, it's strictly less than 1, this is finite. To show that gradient u belongs to LQ, then back to the original problems, I can recover this is the non-homogeneous term of f there. And this gives you the required nonlinear Calderon-Zygmunt estimate for the elliptic problems. Okay, we can further ask that then what is the minimal regularity requirement on the nonlinearity? So the observation is that if we look at the nonlinearity here, this is the Cauchy variables for the gradients. And this is the space variables. We can separate. This is this is a tangential direction, one direction, and this is normal directions. And we see that this nonlinearity is allowed to be merely just measurable in one direction, say like the normal directions, while it has a small BMO semi-norm in the other directions, like say x prime, this is a tangential direction. Okay, then the idea is that like for the linear problems, we are separating the limiting PDE in this way. This is a normal direction here. The other thing, this term is a tangential direction. As you see, we have this is a tangential and a tangential. This is a tangential and the normal. So once we do have this kind of a separating PDE, then we can apply to component type estimate. And then using, so we have this one has a elliptic property. Then we can separate this term is a gradient v in the normal direction. to see that this gradient of V has a real ellipsis regularity. So in this way, we can prove that the limiting PDE has a ellipsis regularity, even the case that it is allowed to be measurable in one direction. Still, this has a ellipsis regularity. So, and then we are going back to the standard approach by using maximal function, and we can still prove that Calderon-Zumwalt estimate. And this is done with my former PhD student, Yu Chang Kim. And this is, of course, this is only for the elliptic case. And another, actually, as I said several times, this maximal function approach is really dependent on the scaling, the standard maximal function. On the other hand, and the Kerloff also employs like a sharp maximal function method, like in a series of papers of obtain, of course, linear parabolic estimates. And this classical maximal function approach relies on the scaling invariance property. And the thing is that it cannot be applied to this kind of non-isotropic elliptic problems like these problems. And then next question is, how about P-Laplacian parabolic problems here? So here we have the gradient with respect to spatial variable, and we have a derivative with respect to time variable. And the scaling with respect to space and the time is not homogeneous. And the constant times u is not actually anymore a solutions. So it means that the maximal function approach cannot be applied in general. So for this kind of parabolic P-Laplacian problems, we need a maximal function free approach or an intrinsic maximal function approach for this P-Laplacian parabolic system. Okay. So to talk about P-Laplacian parabolic problems, we should talk about intrinsic geometry. So Di Benedetto and Friedman introduced the so-called intrinsic cylinders right here. Okay, as you see, you have this parameter lambda. And this lambda is very close to gradient u size or the size of u, in such a way that the scaling parameter lambda and the average of gradient u of this cylinder are coupled by a condition of the time. Right? So the average of the gradient u on this particular intrinsic cylinder is almost lambda. Then my PDE looks like here. This is constant. It means that this is heat equations. So by introducing this lambda and this property under this cylinder, so the gradient u is almost lambda, then it goes to heat equations. So in this direction, there have been many regularity results for the natural generalization of the parabolic P-Laplacian systems, in particular, Lipschitz regularity. Okay. And then here comes the maximal function free techniques. So in 2007, and Esralbi and Minjona actually introduced the so-called maximal function free technique to prove the Calderon-Zumwalt estimate for the parabolic P-Laplacian systems. Okay, the good thing for this approach is that This method produced a purely PDF proof, no tools from harmonic analysis, and show suitable decay estimate for the upper level set of this gradient UP, not the maximal function, based on the use of the scaling compactness argument. Also, this coming from the intrinsic geometry. And then once reached here, then do it, the integration of a level set to provide the desired LQ estimate of the gradients. And this approach is very so influential that it now becomes a classical approach in the literature here. In particular, the PDE without like a scaling invariance property. So move to the non-standard growth. So classical maximal function is not working. So instead, this maximal function free technique is working. Also, if we define the so-called intrinsic maximal function, that it is working also. So actually today, my talk is only focused on the linear problems and nonlinear problems, but it has just a standard growth. And coming Sunday, so I am talking about purely non-standard growth for the including like double page problems and very, very general nonlinear problems. Okay, so I might be stop here, my talk here.